Okay, we have a live review. All right, so let me just post this into the event page into our Schoology. All right, so that's posted in Schoology. That's good. All right. Some things that we will need to cover. It'll be similar to the review that we had on Friday, except for that we have more time. We can go more in depth. I can explain some things. Hopefully you guys will post some questions. See if anybody posts any questions to begin with. That's okay. I should have posted some questions. I forgot. That's okay. As you guys start joining. In the meantime, I want to emphasize the fact that this test is more difficult because of the fact that you have to show your work. So the calculations you have to go through, it's not just this multiple choice where you get to choose the one answer that fits. You need to show the equation, show the manipulation, include the work, include your units. You must include units in all of your steps and your answer the correct units. You must also do sig figs with correct rounding. You will lose probably 1 point on the test at least. I'm gonna guess. I'm gonna try to push for just one point for sig figs, but it's gonna be there. So I'd hate for you guys to lose that point. So this makes this test a little bit more difficult than past retakes you've had, which will make it a little bit more difficult than the actual Thermo test. So you really got to know your stuff. All right, so what I'd like to do though is start off with your essential skills. So let's go to start sharing documents. Let's see if I have them all opened. I'm going to show you a lab that we did last year and the year before. Yeah, you guys can see this. Okay. Oh, wait, no, this is the worksheet. This is not it. Let's try that again. Where is it? I just had it. Specific key lab. Oh, I see. You guys have it, and the wrong one keeps popping up. I apologize. Okay. I have quite a few things open on my desktop. All right. So this was the lab that we gave last year and the year before, and the difference is the fact that we walked you through it step by step, moment by moment. Hey, this is what you need to do. The labs now are pushing more for you need to figure out what needs to happen. You need to figure out how this needs to progress. And it's the thinking part. We want to emphasize the critical thinking more than we've done in the past. So we're getting there. That's important in college, important in your AP classes, and it's going to be important for the next generation science standards as they are rolled out. So thinking through this lab, there are several questions that relate to the lab, and you need to be able to identify the different steps. For example, use the scale to get the mass of your unknown metal. Here, you place the metal in the, well, you know what, let's just skip this part. I think we have good questions down here. Here we go. So here's your beaker of boiling water. And the temperature of the boiling water is 100, right? So can I type in 100? 100 degrees Celsius. Okay. All right. So it's 100 Celsius, which means that the initial temperature, and this is where a lot of people keep getting messed up, the initial temperature has to be 100 Celsius as well. It's been sitting in the water for 5 minutes, so of course it's going to be 100 degrees. Okay, and the water is flowing from the water to the metal, right? If you put something in the water and the water is really hot, it's going to make that object hot. all right? Then, after 5 minutes, that metal is really hot, 100 degrees Celsius. We're gonna drop it in this coffee cup calorimeter. And more than likely, the initial temperature was somewhere around, let's say, 21.5 Celsius. That wasn't necessarily what the temperature was, but let's just pretend like that's what it was. The final temperature of the water, after it had been cooking well, let's say it's 23 cooking. If it had been, you know, it's been in the water for a little while. So, and then the final temperature of the metal is the same as the water. Same as the water. So it ends up being 23.0 degrees Celsius. Okay. Now the heat flowed from the metal to the water. Okay, and you'll notice that the temperature of the metal is now lower than it was at 100, but it's still higher than the initial temperature. So obviously the heat had to go from the metal to the water. So I'm talking about this in regards to essential skill number 1, but it relates to the lab. So this is good because it could give us something to talk about. So let me bring up the bamboo paper and I can write some stuff on it. And we're just gonna, oops, where's my bamboo paper? There it is. We're gonna talk about this in regards or in relation to the lab because I think that will make it easier. So essential skill number 1. So and I've drawn this out multiple times for many people. So beaker, boiling, H2O, okay? And heat flow, we're gonna say, actually, I'm gonna do this like this. Maybe this will help. I say from the water to, and we'll make it like this, the metal, okay? Because the metal was cooler to begin with, all right? And at first the metal's in here. Well, actually, let's just make the metal okay, and the water's in there too. Remember, it's boiling though. All right, so it's boiling. So water, the heat flow is from the water, which is really hot. I'd make it all red, huh? I'm gonna keep my theme here. Water, which is really hot, to the metal, okay? Then your copper, your unknown metal, is gonna go to the styrofoam cup, right? So we get the styrofoam cup. Okay, and it's got a thermometer in there too. Oh, I wish I could draw. I really do. Okay, and then we put the copper, the unknown metal. Oops. Sorry. Oh man, I hate it when that happens. Okay. And so there it is. And the flow here is now from the metal, which is really hot, to the water. The water is the cooler part there, okay? And, okay, so heat always flows from an area of high heat to low heat. Here, the water was really hot, it flows to the metal, gets the metal pretty warm, and that's, of course, at, by the way, that's at, make this green, this is at 100 degrees Celsius. And then this was originally, it was 21, and it was 21.5, and ended up being 23 degrees Celsius, okay? So hopefully that helps you a little bit with that. And say, where are the molecules moving faster? Oh, I did it again. Goodness gracious. So where are they moving faster? Okay. And clearly they're moving faster at 100 degrees Celsius. Okay. So that's essential skill number 1. Important to get. All right, let me get rid of this stuff. Okay. So now we're going to go back and start talking about essential number 2. And essential number 2, this is, it's memorization. Oh my Lord. I'm having problems with my pen. Okay. It's the memorization of page 3 of your notes. That's really what it boils down to. And if I was able to do this, let's see if I can do something else. I don't know if this will help. If I drew a huge graph, here, okay? And water basically flows on this line. So here, goes flat, goes up, goes flat, and it goes all the way up, okay? So we'll say that temperature is increasing along this axis, and heat is increasing along this axis. And it's important to know that heat can do one of two things. As heat increases, either you get the temperature change, right? So either you get a temperature change or you get a phase change. So this, okay, this is, by the way, this is a solid. So here you get temperature change, and that's what's happening right here. Or you get a phase change. Okay, it can only do one of two things. It can't do them both at the same time. Heat cannot change temperature and change phase. It can do temperature change or it can do phase change, but it can't do both. Okay? So then you have solid, here's you have liquid, and here you have gas. And the reason I like this is because you can look at it like this. Essential number 2 is all about phase change. Okay? So it's all about this one right here and this one right here, these two flat lines, okay? So the things that you should take into consideration, and actually let's do this in 2 different colors. Yeah, we'll do it in red. As you are heading this direction and this direction, okay, you're adding heat, okay? So delta H equals positive, okay? This is endothermic. If you are adding heat to it, you are breaking bonds. That does not look good. Okay, this right here specifically is the delta H of fusion. So regardless of what we do, I should make it another color entirely because it doesn't matter which direction you're headed. Let's make it green. We'll make it a nice little neutral in between those two. Actually, purple. What am I saying? Purple's the in between, huh? I think I never studied colors before. Okay. It's the delta H of fusion going both directions. Delta H of fusion because a solid's involved. Okay? That's the delta H of fusion. Endothermic, breaking bonds, positive. Okay? So now if it's the same for both of these when you're adding heat, both phase changes, right? Doesn't matter. Delta H equals positive. You're moving to the right. Okay? It's endothermic. It's breaking bonds. Breaking bonds. Okay? So you're looking at this, and if I was going to draw something, now I can do it in green. I've got these molecules all tightly put together in a solid, and then in a liquid, they start moving apart a little bit, right? They start rolling over. That's not a very good picture. They're close together, but they're rolling over each other. Now there's movement. Here, it was like vibrating in place, right? They're vibrating in place. Okay, so this is what's happening here. There's movement there. There's much more movement. Here, they're really close together. Here, not so much. There's space in between. And then gases are really far apart. They're just zooming around, and there's very few of them. Okay? They're bouncing off walls and all that kind of stuff. Okay, moving very fast. Now, so we've added heat to both of these, from a solid to a liquid. It is delta H of fusion, breaking bonds. Delta H is positive, endothermic. Liquid to gas, endothermic, breaking bonds. Delta H is positive. The delta H is the delta H of vaporization. I'm just going to abbreviate this one. Remember, this one goes both directions as well because a gas is involved. Okay? Now, if we go the other direction, make these light blue. If we go the other direction, okay, now we're cooling down, which is why I use light blue. Now we are forming bonds. Okay, it's losing energy. Forming, I'm having a hard time writing. Forming bonds, delta H is negative. It's exothermic. And it's the same for both of them. So let me draw the arrow first. Forming bonds, delta H is negative because it's losing energy. It's exothermic. Okay, still delta H of vaporization up top and delta H of fusion down bottom, but you have to remember those two. They kind of go between. Okay? Just think about the movement of those molecules. So I'm going to go to the next page and I'm going to put up one of the most popular questions that trips so many students up. Not even funny. Okay? Condensing. Tell me everything you know about condensing. Okay? Give you a second. Think about it. Or you can stop the video. Okay, so here we go. Think about the phases you're going through. Okay, from if you're condensing, it's a gas to a liquid. So if you think about the graph, right? It's the gas to a liquid. So you're going this direction up top here, all right? So that means that you are, and if this is heat, it's going down, delta H is negative. You're losing heat. It is exothermic because exothermic is losing heat. You are forming bonds. And the last question is it delta H of vaporization or delta H of fusion? It's delta H of vaporization because you have a gas involved. Okay. So that's the kind of thing I would ask you on the test. The other way you could look at it is not other way, I'm sorry, other things you can look at. So you should be able to do it for each of them. Okay, what happened? Oops. Surprise, I messed up. All right, sorry. What does it do for melting? What does it do for boiling? What does it do for freezing? Okay, so those are the 4 different phase changes. It could also say H2 plus O2 yields H2O. And the delta H for this is a positive 68.6 kilojoules. Okay. I need to balance it probably. Okay. Is this exothermic or endothermic? And you would say, hey, that delta H is positive. That's endothermic. Okay. You got to watch out for those trick ones where who cares about the reaction? It's about the delta H at that point. Okay. So there's a couple different ways they could have asked essential skill number 2. And those questions are spread out. There's a lot of those types of questions. Essential skill number 2 is a tough one. It's an important one, and that's why it gets hit on so much in the retake. All right, let's go to our next essential skill. Let's go to, we're on to essential skill number 3. And these are the phase change calculations. Okay. So you have to memorize the equation, which is Q equals M times delta H. And that delta H, well, there's two questions. Let me back that up. There's two questions you need to ask yourself. Number one, is it positive or is it negative? Okay. And the way that you'll know is the verbiage. Okay. It's if it's positive, it'll say things like it's heating, it's adding energy, it's absorbing, it is I can't think of them all. Absorbed, added, I don't know. So some of those. If it's negative, the verbiage will be cooling. It will be heat lost, heat given up, heat removed. Okay? If it's positive, you're gonna, and this is all phase change, right? If it's positive, you're going to have it going from a solid to a liquid or from a liquid to a gas. If it's negative, it's going to be going from a gas to a liquid or a liquid to a solid. So these are ways that you can determine if it's positive or negative. The second question you're going to need to answer is it delta H of vaporization or is it delta H of fusion? Okay, so if it's delta H of vaporization, okay, it's either a liquid to a gas or a gas to a liquid. Okay, oops, gas to a liquid. But the key there, let's see if I can get that, is the fact that it's a gas. A gas is involved, okay? If it is delta H of fusion, it is solid to liquid or liquid to solid. And of course, the way you would know that is the fact that there's a solid involved. Fusions are solids, okay? So let's see if we can practice one. I'm going to share a document. I think it's got some phase change calculations on it. It is. Okay, here we go. Good. All right, so let's see. So on this worksheet, it gives you some hints. It has all this information up here, and I'll refer back to that when doing the problem. Let me just jump to something else that has it. Okay. So let's look at number 3. How many joules are required to melt 100 grams of water? Here's the key, melt. Okay, it's a phase change problem. Okay, so we know that we're going to be doing Q equals M delta. I wonder if I can do that here. Oh, you know what? I'm going to do it on my bamboo paper. So let's just remember this. How many joules are required to melt 100 grams of water? Okay, so let me show my bamboo paper again. Okay, so this is number 3 on that worksheet, and let me change my font color. So how many joules required to melt 100 grams of H2O? Okay, all right. So we said melt. So we know it's going to be Q equals M times delta H. Now, let's think about our key terms. We want to know, question number 1, is it positive or negative? Heating, added, absorbing. I just remembered the other one after looking at that question, required. Okay, so we go back to the question, and I see the fact that it says melt and the fact that it says required. So I know that M is going to be times a positive delta H, okay? Second question, let's see if I'm right. Second question was, is it delta H of vaporization or delta H of fusion, okay? So if we're doing that, liquid to gas, that's boiling. Okay, gas to a liquid is condensing. Solid to a liquid is melting. And liquid to solid is freezing. Okay. So let's see what we say here. We've got melt, which means that we're looking at a solid to a liquid, which means that it's going to be delta H of fusion. Okay. So if we solve this problem, Q equals 100 grams times positive 334 joules per gram. Make sure you know these units. And the grams will cancel out, leaving you with Q being equal to 33,400 joules. There's your answer. So hopefully that makes sense to you guys, and there'll be problems like that on the test, most definitely. Let me see if there's I think we can just go right on to, we should just be able to go right on to the essential skill number 4. So let's do that. Is there anything else I want to say about phase change? I don't think so, not right now. Okay, specific heat. I mean, if you're going to talk about a topic that's on the test, with everything that is involved with specific heat, that's probably a third to a half of the test in some way, shape, or form connects to specific heat. So number 4 is specific heat calculations. Now, I'm going to talk about specific heat calculations, but I'm going to keep adding things in about other questions that will be on the test. Okay, so we're looking at Q equals M times CSP times delta T. All right, so let's just look at this from its simplest form. Q, the variable, is heat. M is mass. CSP, that is specific heat. And delta T is change in temp. And in order to calculate a change in temp, you have to remember that it's T final minus T initial. That's what's equal to delta T. Okay, very important. That's going to come in later. The CSP, the units for specific heat are joules over grams times degrees Celsius. Very important. Mass, of course, is grams, and heat's in joules. Now, I didn't go through all of this with the phase change calculations. I probably should have, but it's definitely super important with specific heat calculations. So they could just give you a problem and just say, hey, solve for Q. So let's do one. I'm going to share that same worksheet with you, and we'll just do one. That's it. So, okay, let's look at number 2. How many joules are required to heat 250 grams of liquid water from 0 to 100 degrees Celsius? All right. So when you do this, you can just plug everything in, and it should, like, there isn't so much that you need to kind of figure out what to do as much as it is just understanding which variable goes to which, or which piece of measurement, or which data goes with, not data, which measurement goes with which variable. Okay. So what we had was, this was number 2. How many joules are required to heat 250 grams of liquid H2O from 0 degrees Celsius to 100 degrees Celsius? Okay, so we've got our equation, Q equals M times CSP times delta T. And the words tell you where to go with this. I mean, again, I'm the teacher. I think everything's a little bit easier. So M is mass. So we can say we've got 250 grams. That's the mass. Okay. So 250 grams. The CSP. How do we know which CSP to use? It's based upon the state of matter, liquid water. And if we looked at the top of that worksheet, it would say 4.18 joules over grams degrees Celsius. Okay. And then the temperature change. I told you that was T final minus T initial, which the final one is whatever it goes to. Okay. Sometimes some people like to say it's T2 minus T1, and whatever it goes to is T2. Okay. So we've got 100 degrees Celsius minus 0 degrees Celsius. Now, we said that words like required means that it's going to be positive, and it will be positive, but you don't have to make it positive. It's going to be positive because the temperature change was an increase in temperature, which means a larger temperature minus a smaller temperature gives you that positive. So really this comes out to be, we can cross that out and just say this is 100 degrees Celsius. So what's going to happen is our degrees Celsius are going to cancel out. Our grams are going to cancel out, leaving us with joules, which is good because that's what we want to have. Q is joules. And we multiply these together. And while I feel like I can do some of it in my head, I really don't want to. It will take too long. So I'm going to multiply those three numbers together. And my Q ends up being 104,500 joules. And we look at the problem, and for the sake of argument, let's just pretend there's 3 sig figs. So this would round up to 105,000 joules. Okay, and that would be the answer. That's if it was just Q. That's the simplest form of this essential skill. Unfortunately, this essential skill is not that simple. It could be, there could be several different forms of this essential skill. So let's go to the next form of this essential skill. The next one is, we're going to keep essential skill number 4. What if they ask about what is the CSP? Okay, so if you remember, Q equals M times CSP times delta T. By the way, some people like to call this Q equals MCAT. Q equals MCAT. You can see that M, CSP, delta T, you can see that. Anyways, so let's say they wanted you to do that. So how would you get the CSP by itself? Well, this is the algebra. You have to isolate the variable, divide both sides by M delta T. So the M's go away and the delta T's go away, and you're left with CSP is equal to Q over M delta T. And some students have recognized appropriately that whenever you manipulate the specific heat equation, Q will always be on top. It will just always be on top. Okay. All right. So now let's see if we have. I don't have a problem handy. Actually, that's too bad. If we did the CSP one, it's very similar to the lab, in which we had to calculate the CSP for the unknown. But usually what happens is that this is how tricky this could be. Piece of metal released 805.6 joules, cooling from 95 degrees Celsius to 21 degrees Celsius. Let's say 95.0 degrees Celsius to 21 degrees Celsius. Mass of metal was 45.5 grams. Okay. So when you do this, you would have the CSP is equal to 805.6 joules. Now this gets tricky because you'd say, oh, it's released. So let's go. It's released. Now, if it does the problem like this, that means that that will be negative. So it's negative 805.6 joules, okay, divided by the mass, which we said was 45.5 grams, and the temperature change. It was 95.0 degrees Celsius to 21.0 degrees Celsius. So it's 21.0 degrees Celsius to, or I'm sorry, I drew an arrow. I meant to just leave that as a negative. To minus 95.0 degrees Celsius. And what will happen is this will be negative. So what is that? 21 minus 95, negative 74, negative 74.0 degrees. So this can go away. So what's going to happen is these negatives, change colors here. And a good thing, these negatives will end up canceling out, which is nice. So 805.6 divided by 45.5, and I divide these first and say equals, and then I divide by this. If you do it straight across, a lot of people are making the mistake in their calculator and ending up with a totally wrong number, because they'll divide this and then they'll multiply by 74. If you're gonna do that, make sure you put parentheses around the entire bottom so that you do the order of operations correctly. All right, so and then divided by negative 74. And I end up with my CSP of my metal end up being 0.239, and the units, joules per gram degrees Celsius. Joules per gram degrees Celsius. So don't forget to add in the correct units for CSP. Those units for CSP are huge. You need to have that memorized. Excuse me. Memorize that the units for Q are joules and that the units for CSP are joules per gram degree Celsius. That's really, really important. I just can't emphasize that enough. Okay. All right. And so to continue along with this specific heat problem, there is yet another way it could be asked. And the way that this would, so we're still on social skill number 4. Another way that it could be asked is they could say, well, what's the final temperature? Excuse me, I'm sorry. What is final temperature? And so if you remember right, this is Q equals M times CSP times delta T. Now there isn't a final temperature directly embedded, so you maybe have to do some substitution. We know that delta T equals T final minus T initial. So maybe we could do some substitution. We could substitute this equation in for delta T, which gives us Q equals M times CSP times T final minus T initial. And if that's the case, then we can manipulate the equation. Let's say we divide both sides by MCSP. MCSP, so these M's go in, the CSP's go away. You end up with a T final minus T initial is equal to Q over M CSP. And then you could add T initial to both sides. So the T initials are gone. So you're left with your final equation, T final equals Q over M CSP plus T initial, T1, okay? So at this point, I'd like to show you, we actually have a key. I had forgotten all about this. I'm gonna show you the key, and I believe this is the key to the review, the study guide. I'm pretty sure we have one. Here we go. Number 17. 25.6 gram sample of water is heated from 30 degrees Celsius to some higher temperature. There was no phase change. With the absorption of 3,695 joules of heat, what was the final temperature of the water sample? So delta T, now you can do this two ways. This was done the other way. Delta T equals Q over CSP times mass. So that was 3,695 joules over the CSP, which is 4.18 joules per gram. and then the mass was 25.6 grams. And that equals 34.5 as far as that delta T goes, the delta T. So the delta T was 34.5. T final is equal to 34.5 plus T initial, right, which was 30. That ends up being 64.5. Okay? So that is another way that specific heat is calculated. Okay? All right. So another thing I want to talk about in regards to specific heat is just the concept of specific heat. Now, this isn't directly an essential skill. These are just questions that are asked, of course. And what is specific heat? And this is back to the definitions. You better know your definitions in units, and you can do that. There's the vocab quiz. There's just studying from the notes. Whatever it is, you need to have it down. Okay, so CSP, the specific heat is the energy required, the energy needed, okay, to raise 1 gram of a substance by 1 degree Celsius, okay? So it's because it's the amount of energy, joules, that you get to raise 1 gram of a substance by 1 degree Celsius. So it's like 1 and 1. So if you had, oh, it took us 2,000 joules, or I'm sorry, the specific heat of a substance is 2,000 joules. That means it takes 2,000 joules. I don't even like that one. Let's just do water. I'm making stuff up that's not right. 4.18. It takes 4.18 joules to raise 1 gram of water by 1 degree Celsius. Okay? So let's say you compare water, 4.18 joules, gram degree Celsius. Compare that to what we have, copper, 0.385 joules over grams degree Celsius. And so remember, this is 1 gram, 1 degree Celsius, 1 gram, 1 degree Celsius. So this number, 0.35, is lower than 4.18, which means that I had to add a lot less heat to get this to go up a degree, right? Okay, it took very little energy, okay? So a lot less energy to get it to go up 1 degree, assuming it's the same mass, and it is, right? 1 gram, 1 gram, okay? So water is really high. I mean, you start looking at the list, and the metals are 0.3, aluminum is 0.9, which is pretty high for a metal, but brass is 0.3, silver's like 0.2, gold's like 0.2. So they're all somewhere in that region, but they're not very high. 0.6, 0.5. You don't get a lot going over 1, except for water. I mean, ice is 2 point something, and steam is 1.97. So water is high. Water is very high in its specific heat. It's one of the higher ones we deal with. There, there might be one other one, but I can't think of it right offhand. Water is pretty much the highest that we're going to deal with. Okay, very high CSP. And if you had to compare, we're talking about the elements and simple compounds. If you're going to compare an oven mitt with a metal pan, okay? And there's 2 ways the question can be asked, which is higher, which is lower, right? And if we're just talking about which one has the higher, say higher CSP. Remember, we're talking about the amount of energy it takes to raise 1 gram by 1 degree Celsius. And let's pretend you have 1 gram of oven mitt and 1 gram of metal pan. Which one can you heat up easier? Which one's going to take less heat to make it hot? Well, the metal pan heats up really fast, right? The oven mitt, it takes a lot of heat to get that hot. That's why we use it to take things out of the oven. So oven mitt, ding, 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 much higher CSP. All right. Now, The other question that kind of goes along with this, when we're talking about water, we're talking about high CSP. Really, if we're just going to talk about heat, just talk about heat. And this kind of relates to essential skill number 1. Don't be fooled by temperature. So temperature, definition of temperature is average kinetic energy. Average kinetic energy. And kinetic energy is motion. So temperature is kind of the measure of motion, right? Okay, so you have a lot of motion, you have higher temperature. Okay, but what about heat? Everything has heat. Okay, so the amount of heat something contains is based really upon, I mean, it is temperature, but it's more about how much of a substance you have. Okay, and the Bill Nye the Science Guy one video, we compare a swan, an ice swan, and I'm going to try to draw this because it just seemed like a fun thing to do. That looks more like a goose or a something. Anyways, so this is ice. Oops. Oh, and I just ruined my swan. I spent so much time making it. Okay. And then there's a match, and the match is on fire. Okay. Which one has more heat? Which one has more heat? Okay. So okay. And so it might not make a lot of sense. I mean, the ice swan is really cold, and the lit match is really hot. But the number of molecules is more in the swan. I mean, if you think about the heat, you think about like, what's it going to take to make some changes? And that little match is not going to melt that whole swan. It's going to, all its heat's going to be used up and gone before it can ever do that, okay? So the more molecules equals more heat. And so this comes to the question in your notes is Pacific Ocean versus pot of boiling water. Okay. And most obviously, there is more heat in the Pacific Ocean because there are way more molecules. Okay? I just can't emphasize that enough. All right. So those are the essential skills and some key things from the notes, key things that are frequently missed questions. So I want to make sure that I talk to you guys about that stuff. I think the next thing we should do is finish off the lab, and we started talking about that. And so I think we should go back to it. And there it is. All right, let me share it on the screen with you. Okay. So we talked about the water, we talked about the transfer of heat, and look right here. So what was the purpose of placing the metal in the boiling water? Obviously to heat to 100 degrees Celsius. What happened to the metal when it was placed in the colorimeter? It heated water, heated the water. What happened to the water in the colorimeter? Heat the water and cooled, and metal cooled down. And then what happened to the water in the colorimeter after the metal was added? Water warmed up. Where did the heat use to raise? Okay, so this is the key thing. Where did the heat use to raise the temperature of the water in the calorimeter from? From the metal, right? So this is what we're talking about. This is a closed system. So as much as that water warms up, the heat that was required to warm that water up came from the metal only. There was nothing else. We didn't do anything else to that cup. How else could that water have gotten warm? We did nothing else to the cup, which means that the only way that water could have warmed up is if it came from that piece of metal, all right? And the only way that the metal could have cooled down is if it could have given that heat up to the water. So when we compare those amounts, we say this over and over again, right? Amount of heat lost equals amount of heat gained. And the amount of heat lost is negative, and the amount of heat gained is positive. Not to be forgotten. Okay. So you're going to be given some data like the mass of the water, the CSP of the water, the delta T. And is there anything in the, I don't know if this, this must have been an older mixture review sheet because it doesn't do anything for the lab, which is okay. So let me, I think that was all we did. Okay, so let me create a little sample here for you guys and the bamboo paper. Okay. All right. Lab. Okay, so that maybe the mass of the metal is 65.0 grams, and the mass of the water is 250.0 grams, and maybe the the boiling water. Boiling water was 100 degrees Celsius, and you want to know. Maybe there's some blanks. I don't know exactly. I can't remember exactly how we're going to phrase this. We might give you the delta T, or we might ask you to find the delta T. So temperature, or let me do it like this. So initial T of metal, final T of metal, and initial T of water. I think we're going to say that one is 17.0 degrees Celsius. And let's say that I think we have to give you this too. Final T of water is 22.0 degrees Celsius. And I'm totally making up all these numbers, by the way. So then you would have to go in, though. This is the part that you'd have to do. The initial temperature of water is actually the same as the boiling water. So it's 100 degrees Celsius. And the final temperature of the water is the same as the final temperature. I'm sorry, the final temperature of the metal is the same as the final temperature of the water, which is 22.0 degrees Celsius. Okay, and we'll provide you the rest, of course, in a table. So there's two ways to solve it. My preferred way, you don't have to do it this way. The preferred way that we set you guys up to do is to set the two equations equal to each other. Using the Q equals M times CSP times delta T. And so there are two of them. There's one for water and there's one for the metal, because there is heat gained and heat lost. Okay, so actually I'm going to give you guys a second. I'm going to take a sip of my drink, and you guys some Mountain Dew, keep me awake here. And you guys see if you can start this. Okay, that's good. All right, so my preferred way is to set the equations equal to each other. Gained and loss. Oh, gracious. Oh, wow, what in the world was that? All right. It suddenly made a huge swath of erasing. That's all right. You guys know what I'm doing. Q. No. Sorry, that totally got me off track. Hitting the wrong button on my pen. Mass times CSP times delta T, and this is the one for the water, is equal to mass times CSP times delta T, and this one's for the metal. All right, so we don't have the CSP of the water. That's the only one we don't have. We have the mass of the water. That was 65.0 grams. The CSP of the water, which we give you in the beginning of the test, 4.18 joules over grams degrees Celsius. And the delta T of the water, which was, we gave you 22 minus, 22.0 degrees Celsius minus 17 degrees Celsius is equal to the mass of the, sorry, I didn't read my things very carefully. Sorry, the mass of the water was 250.0 grams. Okay, because the mass of the metal was 65.0 grams. We don't have the CSP, and the delta T was the final, which was 22, minus the initial, which was 100. 22 minus 100 degrees Celsius. Now, that's going to make this negative, right? And we can't have a negative CSP. So what we're going to do is we need to recognize that the metal, it lost. So that's a negative. That means that this is negative. Okay. And those are going to cancel out. These are going to cancel out. So 22 minus 100 ends up being 78 degrees Celsius. So if we isolate for CSP, we divide both sides by the M delta T of the metal. CSP ends up being equal to 250.0 grams times 4.18 joules over grams degrees Celsius times, we go ahead and subtract those, 5 degrees Celsius, all divided by 65.0 grams times the delta T, which we said was negative. I forgot what that. And that we're going to make that negative 2 out here. Negative 78 degrees Celsius. Okay, so I plug all that in. 250 times 4.18 times 5 divided by negative 65, enter, and divided by negative 78. All right. And so our unknown, our CSP, ends up being equal to 1.03 joules per gram degrees Celsius. Okay. And so that is one way you could solve it. Now, you can not only solve it that way, you can also solve it by solving for Q of water first. I'll show you what that looks like. If we solve for the Q of the water first, Q of H2O, then we have the mass of we have mass times CSP times delta T. So Q of the H2O is equal to, I can't remember my own numbers, 250 CSP delta, okay. So it was 250.0 grams times 4.18 joules over grams degrees Celsius times the delta T, which ended up being 5 degrees Celsius, okay, when you subtract them out. So 250 times 4.18 times 5, that Q right there Q of the H2O would equal positive 5225 joules. The grams canceled, the degrees Celsius canceled, joules. Okay? And if you remember, the heat gained is equal to the heat lost, but that the heat lost has to be negative. So that means the Q of the metal is now equal to negative 5225 joules. Okay? And we have the Q of the metal equals mass times CSP times delta T. And we're solving for CSP, so we're dividing both sides by m delta T. These cancel out. So we end up with CSP is equal to, oh, that's negative. Negative Q metal over m times delta T. And that was negative 5225 joules. The metal was 65 grams, I believe that was it. And the delta T was negative 78 degrees Celsius. Just to make sure. Yeah. Okay. And all that ended up I believe, being 1.03 joules per gram degree Celsius. Yay! All right. Okay. So hopefully you guys are tracking with this and understanding what's going on. Last piece would be, I know we're going over a little bit and I apologize. I just want to talk briefly about Hess's law. Okay, so I have a worksheet for that. I have a couple worksheets for that, actually. Let's do one. I've got a fun one. There we go. Okay. So let's do this one right here. We're going to calculate the reaction 2 aluminum plus 3 chlorine, yields 2 aluminum chloride from the data. And we have 4 equations. Oh my gosh, so much, but that's okay. Okay, so I can't show this and my Bamboo tablet at the same time, unfortunately. So I'm gonna try to copy it down for you so you can see it. You know what, I have to be honest with you, I don't really want to do one that big. Let's do something easier. Let's do number 3. There's fewer equations to do. Hydrogen gas plus carbon plus oxygen yields ethanol. And that's what that is, C2H5OH, that's an ethanol. So it gives you these 3 equations, something shorter. I'm getting tired. Sunday night, I want to go to bed. Okay. All right. This will be the last thing we do. Okay. So we are trying to get, I'm just going to put it down here. We're trying to solve for 2H2 as a gas plus 2 carbon as a solid plus O2 as a gas yields C2H5OH, which is a liquid. Okay, so the first equation we're dealing with is C2H5OH liquid plus 2O2 gas yields 2CO2 as a gas plus 2H2O as a liquid. And its delta H is equal to negative 875 kilojoules. So the way we solve this, first step is finding the thing that is only the solo substance, the thing that's in the first reaction, it's not in the other 2. And probably doesn't help very much if you can't see the other one. So I'll go ahead and write those other ones out real quick. Second one, carbon is a solid plus oxygen as a gas yields CO2 as a gas. And the last one is H2 as a gas plus 1/2 O2 as a gas yields H2O as a liquid. Okay. So looking at this, I would say that the C2H5 is not found in the other two, and it is a reactant in the first step, and it's a product in the final. So we're going to need to flip that whole equation. If you reverse or flip a reaction, you must flip the delta H. So that means we're going to have, I'm going to go write this out, 2 CO2 as a gas plus 2 H2O as a liquid yields C2H5OH as a liquid plus 2O2 as a gas. Okay? And if we did that, that means its delta H is equal to positive 875 kilojoules. All right. Second equation, carbon as a solid is not in the other two equations. It's a reactant here. It's a reactant in the first one. So that's actually kind of nice. So that means I'm going to leave it as is. What's interesting, though, is that there's a 2 in front of the carbon here in the final equation, and there's not a 2 in front of the carbon there. So I'm going to have to multiply that delta H by 2. So I'm going to do this whole reaction by 2. So it's 2 carbon as a solid plus 2 O2 as a gas goes to 2 CO2 as a gas. And its delta H was a negative 394.51. If we multiply a reaction by 2, we have to multiply the delta H by 2. So the delta H becomes, it was a negative 394.51 times 2. So now that's equal to negative 789.2 kilojoules. We're out of room over there. Okay, final equation. Things that are in this reaction, they're not in the other ones. Looks to me like the H2, actually. There's no H2 in any of these other ones. It's a reactant here, and it's a reactant in the final equation. It's also multiplied by 2. So we're going to have to multiply this one by 2. So we get 2H2 as a gas plus 2 times 1/2 means it's going to be basically like 2 over 2 O2s as a gas. And that gives you 2 of the H2O as a liquid. Okay? And its delta H was negative 285.8. So we're going to multiply that times 2. Negative 285.8 times 2. And I get that delta H is equal to negative 571.6 kilojoules. And let's just make sure that these cancel out correctly. There's, did I do that? I think this arrow was in the wrong spot. Oops. The final equation, oops, this, sorry about that. Let me change this real quick. Was it? Oh, no, it's not. It's not. Oops, I'm totally messing it up. Quit messing it up. Okay, oops, and now it's green. Does me no good. Let's try this again. Plus O2. Okay, so I try this again. Green. Okay, so the 2 H2s right here. Okay, the 2 carbon is right there. This O2, there's 2 O2s here and there's 2 O2s here. They cancel out, leaving me with the 2 over 2, which is 1 O2. And the C2H5OH is right here. So the rest of the stuff must cancel out. Let's see, 2 CO2s, 2 CO2s, 2 H2Os liquids, 2 H2Os liquids. Oh, that works out fine. So my final delta H. Now, and delta H's are just adding all of the step delta H's, all the intermediate steps delta H's together. So let's see. I've got positive 875. So 875 plus the negative 789.2 plus negative 521.6. And my answer is negative 485.8 kilojoules. So let's go back and take a look at the Hess's Law worksheet and see if that's right, because it actually has a key in there. There we go. And so it's this number 3. Number 3 down here. There it is. Negative 46 exact kilojoules. So the first one was flipped, so negative 1, or just multiplied by negative. You change the sign. The second 2 were both multiplied by 2. And 46 is the round version of negative 485.8. Yay for us. All right. That's all that I have the energy for at this point. Hopefully that was a review that you guys will be able to use. So, all right. Hopefully you guys had a decent weekend. The test is in 2 days. You guys should be able to do that. Making sure you guys go over your notes, study, come and ask questions. I will take, I'll post the answers to the review, the study guide. I'll put it up. I don't know if it's this year's or past year's. I'll just put it up and you guys can take a look at it. All right. Have a great night, and I will see you guys very soon. Get some sleep.